Hallo und herzlich willkommen hier zum Finale der SPL. Bis hierher haben beide Teams lange Nächte gehabt, wenig Schlaf. Wir sehen in Schwarz Biomen, in Blau das Now-Team HTWK. Biomen kommt aus Bremen, HTWK aus Leipzig und beide haben eine Neuigkeit von diesem Jahr umgesetzt: eigene Trikots. Anstoß hat anscheinend Biomen. Und neu dieses Jahr ist auch die Detektion des Anpfiffes. Das bringt ein paar Sekunden, in denen man frei agieren kann. Oder frei agieren kann, sollte es das andere Team nicht erkennen. Und das sieht gut aus. Beide Teams haben es erkannt. Zweikampf jetzt in der Mitte. HTWK kann sich im Moment durchsetzen. Jetzt ist der Ball zwischen den Füßen. Das darf nicht sein. Freigespielt. Die 4 muss jetzt weiter ran. Zwei Bremer Spieler stehen jetzt davor. Versuchter Pass, das hat nicht geklappt. Die
In this video, we're going to go through and build a really strong MA4825 linear actuator as an example build. You can see how if you combine these together, you can make all sorts of machines. This uses the new MA23 threaded rod plate. Uses extreme solid V wheels, really strong, very rigid, and it's just a really simple build. So we'll go through and build this, and hopefully it'll inspire some ideas. So let's get started. I'm going to build this using the 300 millimeter lead screw, but of course you could build this up to say 1,000 millimeters if you'd like. Everything you need to build them. However, since on this particular build we're using metric, we're not going to need the 1/4 inch spacer that comes with the wheel kit or the 25 millimeter screw. We could save these for another project. And sometimes it won't, like this one. So you might need to get a screwdriver. We're going to add the wheels. On one side, we'll be using the wheels that just have the standard spacers, the 6 and the 3 millimeter. I'm just going to push this down. And at this point, I think it's safe to tighten down. Okay, that looks good. We have both on. And once again, I did not fit between our lead screw and the nut block. Just make sure that we can manually put it in there, and we can. That's really nice. This back off, and we'll work on to the next step. Okay, so in this step, we're going to install the nut block onto the plate. You're going to need two 15 millimeter M5 loads. Make sure that your eccentrics are facing, out, away. And make sure that there's no movement whatsoever. As you move it around here, it's nice and tight. But you just have to make sure you cut it a little bit shy so that you have enough here, a little over 20 millimeters, so that you have enough to fit in both ends. I've already cut this down to left to the 200. And all I'm doing is, as I drill it in here, if it starts to get tight, I just stop and hit reverse. Right there, it's a little tight. I'm reversing. Back put it on there, and it's not tight. It's loose right now. Take another screw on the other side here. Back that off a hair. To bring in the lead screw, and we're just going to thread this through a little bit. It's going to be a little bit tight, but just work it through and make sure your set screws in, but not through. That looks good. At this point, I'm actually going to take and turn this lead screw a little bit more and bring this carriage back. It's almost touching this lock collar. Just something like that. And we're going to go ahead and tighten. That's pretty good. I tightened it down, but it's, I'll loosen it back up. Once again, to get the proper height here, what we're going to end up doing is bringing this assembly forward. Let's go ahead and lift up the rod and put the bearing where it goes to set it. And then I'm going to bring this down here by turning this. You can chuck the drill onto the end again. I'll do it real quick. Just to bring it down. Okay. Can loosen this plate up a little. We have a little bit of movement here, and that is due to the fact that we left this loose to kind of study that a little bit. And we'll get busy doing that now. Loose. Just going to go through and start with this top one. Slide that through. Put that on. And then decide where you want your wire orientation. You might want it to the left, to the right. You might want it facing out this way. I'm going to face mine down, probably to the back like this. And slide that in. Down as well. Three, linear actuator, really simple, quick and inexpensive build. I think you'll appreciate the amount of power and precision that you can get out of this system. You could see how you could incorporate two of these systems to make an XY system, a very powerful XY system. You could even incorporate it this way. There's multiple possibilities and opportunities for this actuator. Please be sure to check out openbuilds.com
You're going to hold one end, and I'm going to hold the other end. And now what I want you to do is look at me, look up at me, and I want you to move that way. You got a little bit of a bend in the rod. Now look back at your rod. Look back at this rod right here. Try and get that straight so it's not bent. And then come towards me a little bit, a little tiny bit, a little bit, stop. Okay? Now put a bend in it. Put a bend in it like that. Okay. Good. Now go back to straight. Make it straight. Very good. Now put a bend in it the other way. Okay. Now straighten it out again. Okay. Now I want you to go down. Lower your end. More. More. Okay. Stop right there. Okay. Now I want to back out. Smooth this out. Okay. Release.
ということ。2本の足を交互に出して歩く。段差や階段を上る、降りる。凸凹な道や坂道を歩く。歩くといっても、実は人間はさまざまなバランスを足でとって歩いているのです。だからロボットにとってはとても難しいことなのです。その2本の足で歩くということを世界で初めて実現したロボット、それがアスムなのです。
今、私は足の裏のセンサーで階段を確認し、細かくバランスを取ります。皆さん、ついていないでしょうけど、人間も目を見て、速さに合わせて足の裏でバランスを取りながら、
それではご見学中のお客様、
in a manufacturing facility repeat the exact same movements over and over? How does an automated milling machine move with such precision? It's all because of the stepper motor. What's special about the stepper motor is that it can control the angular position of the rotor without a closed feedback loop. It is a simple, accurate, and open loop system. Let's first understand how the variable reluctance type of stepper motor works, which is the simplest one. Later on, we will move to a highly accurate and commonly used motor type. This motor has 6 stator teeth and can be energized with 3 separate DC power sources. The rotor is made of a stack of steel laminations. It has a different number of teeth than the rotor, 4 in this case. This is done intentionally so that only one pair of rotor teeth is aligned with the stator at a time. You can explain how this stepper motor works by yourself. If you de-energize coil A and energize B, it becomes clear that the rotor will rotate as shown. From the geometry, it is clear that the one-step size is 30 degrees. To get the next step, de-energize coil B and energize C. After that, coil A becomes energized again. In short, the rotor moves to the position with the least reluctance. The step size of this motor is 30 degrees. You can improve the accuracy to 15 degrees with a small trick. When coil A is energized, the rotor is in this position. We know that when coil B is energized, it moves 30 degrees. What happens when coils A and B are energized together? The rotor will come to a position between these two cases, or it will move 15 degrees. After this, de-energize A. Then, after reaching B, energize C as well. This kind of operation is known as half-stepping. The motor we have been discussing is called a variable reluctance motor. The most versatile and commonly used stepper motor is the hybrid motor type. Let's explore the functioning of a typical 1.8 degree step-size hybrid motor. The hybrid motor has an axially magnetized rotor with toothed steel caps. So one end of the rotor becomes the north pole and the other end becomes the south pole. The accuracy of this motor lies in the clever arrangement of the rotor and stator teeth. Let's understand it first. The rotor has 50 teeth. To understand the stator teeth arrangement, first assume that the stator has 50 teeth as well. However, the stator actually has 2 fewer teeth than the rotor. So we are left with 48 teeth. Let's arrange the 48 teeth into 4 group pairs as shown. Now let's realign these groups. The green set moves so that it is half aligned with the rotor. The teeth of the yellow group are completely unaligned with the rotor teeth. The blue group is half aligned with the rotor. The red group remains in place. In short, the red set is completely aligned with the rotor, while the yellow set is unaligned. The other 2 sets are half aligned. Please remember that the rotor end facing you acts like the south pole. The stator coils are connected as shown. They are 2 independent coil sets. When set A is energized, the stator forms a magnetized pattern as shown. One pair of stator poles acts as the north pole and the other as the south pole. As the opposite poles attract, they will be aligned. The same polarity poles will be unaligned. When the coil B is energized, observe what happens to the rotor. It has to rotate by a small angle in order to align with the new north pole. It is clear that this angle is 1/4 of the angular pitch. In other words, the rotor moves by 1.8 degrees. Next, set A is energized with the opposite polarity.
You can find DC motors in many portable home appliances to run under both AC and DC power sources. To know more, in order to make the operation more reliable, more efficient, and less noisy, the recent trend has been to use brushless DC motors. They are also lighter compared to brushed motors with the same power output. The brushes in conventional DC motors wear out over the time and may cause sparking. Thus, the brushed DC motor should never be used for operations that demand long life and reliability. Let's see how a brushless DC motor works. The rotor of a BLDC motor is a permanent magnet. The stator has a coil arrangement as shown. By applying DC power to the coil, the coil will energize and become an electromagnet. The operation of a BLDC is based on the simple force interaction between the permanent magnet and the electromagnet. In this condition, when the coil A is energized, the opposite poles of the rotor and stator are attracted to each other. As the rotor nears coil A, coil B is energized. As the rotor nears coil B, coil C is energized. After that, coil A is energized with the opposite polarity. This process is repeated and the rotor continues to rotate. A humorous analogy to help remember it is to think of the BLDC operation like the story of the donkey and the carrot, where the donkey tries hard to reach the carrot, but the carrot keeps moving out of reach. Even though this motor works, it has one drawback. You can notice that at any instant only one coil is energized. The two dead coils greatly reduce the power output of the motor. Here is the trick to overcome this problem. When the rotor is in this position, along with the first coil, which pulls the rotor, you can energize the coil behind it in such a way that it will push the rotor. For this instant, a same polarity current is passed through the second coil. The combined effect produces more torque and power output from the motor. The combined force also makes sure that a BLDC has a beautiful constant torque nature. With this configuration, two coils need to be energized separately, but by making a small modification to the stator coil, we can simplify this process. Just connect one free end of the coils together. When the power is applied between coils A and B, let's note the current flow through the coils. It's just like the separately energized state. That's how a BLDC works. But you might have some intriguing doubts in your mind. How do I know which stator coils to energize? How do I know when to energize it so that I will get a continuous rotation from the rotor? In a BLDC, we use an electronic controller for this purpose. A sensor determines the position of the rotor, and based on this information, the controller decides which coils to energize. Most often, a Hall effect sensor is used for this purpose. The BLDC design we have discussed so far is known as the outrunner type. In-runner BLDC design is also available in the market.
이게 빅투에 있었나? 그러니까 落とし方が絶妙だよね。
This industrial robot needs a drive with particularly high demands. Not only does the robot have to be able to accelerate and decelerate fast, also precisely positioning is required. In fact, here is a 3-phase servo motor installed. In this video, we will clarify the terms servo motor and servo drive in general, then the 3-phase servo drive. The servo motor is a part of a servo drive, whether brushless DC motor, synchronous, or a robust asynchronous motor. But one thing in common is the detection of the rotor position by a sensor. This can be a resolver or an encoder. In this case, you see an incremental encoder. This sensor device gives feedback to a controller to keep, for example, the rotational speed or torque constant, or to reach the target position as fast as possible. The servo motor system includes the servo motor with its feedback device, a servo amplifier, and a controller. But how do these devices work together? The servo controller sends low-voltage control signals for position, speed, or torque to the servo amplifier. Now these commands are amplified up to high power, which the motor can use. The electrical pulses of a sensor are sent back to the amplifier. This amplifier uses this information to control speed and rotor position. The job of the servo motor controller, also named as the motion controller, is to close the loop on the system by constantly interchanging data with the servo amplifier. The motor parameters like torque, speed, or position can be adjusted immediately. Some manufacturers offer modules, which combine the controller and the amplifier, so you would have fewer parts, fewer connections, and a smaller footprint. Talking about an AC servo motor, you usually mean a 3-phase synchronous motor whose rotor field is excited by permanent magnets, so you get a very powerful and brushless motor of small size. The stator winding produces a rotating magnetic field, whose rotating speed and force is controlled by the amplifier and controller. In order to position quickly, all these motors must have a low moment of inertia, which can be achieved by an elongated shape. The functioning of a synchronous motor was already explained in another video of our Learn channel. Please check.
Encoder is a device that converts linear or rotary movement into digital or pulse signals. The most common type of feedback device is the absolute optical encoder. An absolute encoder consists of the 4 major components: a rotating encoder disc, a light source such as an LED, a photodetector as the light sensor, and a signal conditioner that converts the signals into square waveform. The encoder disc consists of a series of opaque and transparent tracks mounted to a rotating shaft. The tracks of the disc are arranged concentrically around the center of the shaft. Photodetectors assigned to each track designate the resolution of the encoder. The higher the number of concentric tracks, the higher the accuracy. A light source located on the opposite side of the photocells passes light through a capture plate. As the encoder disc rotates, light is either transmitted or blocked according to the pattern. The received light provides a 4-bit word that indicates position of the actuator or device the encoder is mounted to. The most common types of numerical encoding are decimal, binary, and gray code. In a 4-bit encoder, there are 16 unique combinations or numeric code every 22.5 degrees. Gray code is designed where only one bit changes at a time, contrary to a binary system where one or more numbers change in the word. By changing more than one number of the word at a time in the binary system, the possibility of positioning errors is greater, leaving gray code the preference in precision applications. For robot applications, absolute encoders are commonly used for precise positioning operations. The actuator in this example demonstrates the function of the absolute encoder in operation. As the actuator moves to push the carton, the encoder provides feedback that it has reached the user-defined position. The actuator then moves back to the home position, verified by the encoder, and completing the cycle. Using feedback devices closes the loop in motion control systems.
Animation, you get the function of an absolute rotary encoder, as well as the principle of a multi-turn encoder. Rotary encoders are also named as shaft encoder. Measuring systems which use this type of encoders can be classified as indirect and digital. The absolute encoder has a coded disk. As an example, you see here the binary code. The construction of an absolute encoder is more complex compared to an incremental encoders, as they require a decoder. But the big advantage is that each angular position of the shaft can be read at any time, even after a power failure. That means there is no counter value to lose. Counting the number of revolutions with a multi-turn absolute encoder. This example shows a two-stage multi-turn encoder with a
Rotary absolute encoders consist of a translucent disc with a binary pattern etched on it. The pattern consists of a series of opaque and transparent slots. The slots are arranged in a concentric circular fashion, and the number of slot sets is the same as the number of photocells used in the encoder. A light source is located on one side of the strip, while photocell detectors are placed on the other side. The rotary absolute encoder shown here has 3 sets of slots and hence uses 3 photocells. As discussed earlier, with 3 photocells, an absolute encoder can detect 8 unique positions. In other words, the full shaft rotational angle of 360 degrees can be divided into 8 angular intervals of 45 degrees each that can be uniquely detected by the encoder. Here is another view of the 3-bit rotary encoder. If a more accurate measurement is needed, then an encoder with more data bits can be used. As discussed earlier, this means using more photocells in corresponding circular slot sets. Typical rotary absolute encoders have 8 or more photocells. The encoder disk shown here is from a rotary gray code 8-bit absolute encoder.
Design makes it 100% immune to any electromagnetic interference. Micronor's novel fiber optic position sensor consists of a sensor and a controller. The system is connected by a duplex fiber optic cable. No electrical connection to the sensor is required. There's one fiber optic strand for transmitting light to the sensor and one fiber optic strand to receive the light with the position information from the sensor. A push-pull fiber connector makes connection to the controller simple. An LED status indicator confirms that the connection to the sensor is completed and that the system is functioning properly. The model MA4825 is a true absolute position sensor with an incredible resolution of 13 bits. The controller transmits a burst of light to the sensor. Inside the sensor, a code disc modulates the spectral components of the light. The position information is now imprinted in the optical spectrum of the light and guided back to the controller for position readout. The system keeps accurate track of positions to speeds in excess of 2,500 RPM. This is an absolute position sensor. Single turn with a 360-degree continuous reading and a resolution of 8,192. It keeps track of speeds in excess of 2,500 RPM. To demonstrate that this sensor is truly absolute and capable of giving accurate readings at startup, we will now power down the system and start it up again. First, note the position readout of 1,457. The field below shows the angle calculated in degrees. Now, we unplug the fiber optic cable, shut down the software, unplug the power to the controller, and remove the serial interface cable. To start up the system again, we plug in the serial interface and restore the 24-volt DC power to the unit. For now, we leave the fiber optic cable unplugged until the readout software is running. While the sensor is disconnected, the maximum readout of 8,191 will appear. Now, we reconnect the optical fiber and the readout will return to the 1,457 position. The sensor will always know its exact position, whether the shaft is stationary or rotating. The controller is powered by a 24-volt DC and consumes only 70 milliamps. Numerous position output interfaces accommodate many applications. The sensor is unaffected by electromagnetic interference, lightning strikes, electrical discharges, energy weapons, magnetic fields from motors, and radiation. The positional information is embedded into the light spectrum and not the amplitude. Thus, it's unaffected by a varying loss in the fiber optic lines. This wave graph shows the reading of the sensor. When the optical power changes, as simulated here by adjusting the connector, one can see a drop in the readout waveform. However, the position reading is not affected at all. Rather than using light intensity, Micronor ingeniously utilizes the light spectrum as an information carrier, making this a very robust position sensor. Again, note that the position readout does not change when the light amplitude is brought back to the previous level. The MA4825 is an absolute position sensor, immune to electromagnetic interference. It will not radiate or spark, and operates reliably with fiber optic cable lengths of up to several hundred meters. So when true position is needed, Micronor is the solution.
A rotary encoder, also called a shaft encoder, can be used in positioning and motor speed feedback applications. In this video, we explain the function of an incremental rotary encoder. Incremental rotary encoders use discs which contains transparent sections that are equally spaced. A light-emitting diode serves as sender and its light is detected by a photodetector. Therefore, the encoder can generate a sequence of pulses. The output is measured in pulses per revolution, which can be used to determine either the position or the rotational speed. To detect the rotational sense, the encoder needs two tracks. The sense of rotation determines which signal coming from track A or track B is leading. Here, you can see the signal form coming from clockwise rotation. To have a comparison, you see now the signal form coming from counterclockwise rotation. Now the signal coming from track B is leading. It is now up to the electronics to evaluate these signals.
The acceleration sensor combines two components in its housing, a signal processing chip and the actual micromechanical sensor. This cone-like structure is the characteristic feature of such a sensor. The blue part of this structure is movable. This part is deflected during acceleration and deceleration. The result is a change in the capacitance between the electrodes. This change is measured by the signal processing chip and converted into an output signal.
Now notice that while my phone is resting, we have an acceleration value in the Z direction. That's because gravity is actually affecting the sensor. And as you might know, gravity is 9.8. So we're getting a value of 9.4, which is pretty close. So just keep in mind that gravity also affects the value of your accelerometer. So let me move the phone around just to show you how it changes the values. So that's the application. Let's go ahead and take a look at the code.
We're scientists, right? That's our job. And so data is everything, and reliable data, repeatable data, that's paramount. And so if we have a sensor we can't trust, it undercuts the whole process. So we need to have data we can trust, and we have sensors we can trust.
That quality has to be perfect if we're depending on the robot to do its job correctly every cycle, day in, day out, year in, year out.
One of the things that makes robotics really function is repeatability. or precision. What the force torque sensor from ATI gives us is both accuracy and repeatability.
The force torque sensor is a device that uses silicon strain gauges and converts mechanical loads into forces and torques, and it measures simultaneously in all 6 axes, force XYZ and torque XYZ. When you look inside the ATI force torque sensor, you can imagine it resembles a wheel with an outer wall, with an inner hub, with spokes or beams connecting them. Each beam has 4 silicon strain gauges that function in pairs to form half bridges. The output of the transducer is 6 channels of strain gauge voltages. The output is digitized and then converted to force and torques through a matrix calculation. ATI uses very sensitive silicon strain gauges to maximize gain, greatly reducing signal noise. The high gain in the strain gauges allows the beams to be extremely strong, providing very high overload protection. Proprietary bonding methods used during the mounting of the strain gauges greatly reduces hysteresis, which can be a problem for load cells.
The benefit of using a force torque sensor versus a single axis load cell is that you get a complete picture of everything acting on that transducer instead of just one snapshot of a measurement.
The ATI sensor can measure loads that are applied in any orientation on any axis. ATI force torque sensors can withstand overloads between 5 and 20 times the rated measurement range.
As a robot company, we have to be ahead of the curve, or try to be ahead of the curve. The good thing about ATI is they are ahead of the curve. Their force torque sensors are rated well beyond what the robot is spec'd at for payload. Let's say, for example, communications protocols and buses, ATI always seems to be right on line, right on track with what the industry needs at a particular point in time. So we don't really have to spend a lot of time asking ATI for features and functionality.
Our customers all have different environments where they need to use our sensor, so we have developed interfaces to work in every one of them, whether it's NetFT, which will communicate Ethernet data, or DAC-FT for connecting to data acquisition hardware, or the controller FT for standalone operation, and even our newer wireless FT and EtherCAT FT.
This product is being used in every major university in the United States and throughout the world. It's also used in every major manufacturing facility around the world.
The force torque sensor allows them to provide robots with a sense of touch, a sense of feel, that allow them to do applications normally done only by humans.
The most important thing force torque sensing gives us is the ability to open up the robot to other applications where we normally wouldn't have that ability.
Some of the more common applications for force torque sensors are product testing, life cycle testing, control of robots for surgery.
The robotics technology with the full 6 degree of freedom control gives you a lot of freedom that you never had before, because you need to be able to measure 3 forces, 3 torques to get the full loading state of any joint. And that's true for any joint. Once you establish that, you've established the full loading state of any specimen of any joint you want to do.
The coolest thing by far that the force torque sensor is being used for are groundbreaking applications, doing things that no company has ever done before. When we work with our space-related customers, or we work with people doing microsurgeries, things that haven't been invented yet, and we're able to be a part of that process and go through the journey with them to develop their product. Really, whatever the customer needs, ATI is able to provide.
So the support I get from ATI is really great. They have all these products, so it's really nice. That's kind of a one-stop shop. So we're using ATI and have no reason to change. It's a good product, so we keep using it.
Coming from manufacturing myself, I know the importance of reliability and uptime. When we order a product from them, everything comes complete. Software, cables, hardware, take them out of the box, and we're up and running in 20 minutes.
We like using ATI force torque sensors here at ABB because of their robustness, first of all. They are proven, they've been validated by us, and by the customers. Customers know them by name. They have a reputation.
Our trust in ATI has to be the highest possible because the quality and performance of the ATI product and its reliability is a direct reflection of how well our robot can do its job each and every time, and ATI is absolutely a critical part of that.
With the continuing innovation with ATI and their engineers at their facilities, they are not stopping at what they have today. They're continually looking to meet and exceed customer expectations today and for tomorrow's use.
Reliability of the force torque sensor is extremely important to ABB because our name is on that robot. We have to have very reliable end-of-arm tooling, and ATI gives that to us with their force torque products.